We just saw the definition of the naive Bayes classification model, and now I'd like to tell you a little bit more about some other aspects about this model. So the first thing is how to choose this family p theta. So some common choices for this family. Remember that in our naive Bayes model here, we were assuming some family of distributions p theta, as theta ranges over some space of parameters. And so what should we choose? So to do this, we have to first define a model. We have to define this part, the probability of the y's, the marginal distribution, and then we have to define this conditional distribution of x given y. And this factors into each of these, so we just need to define each of these and y, the distribution on y. So first, let's think about the marginal distribution on y. So for the y part, we have this marginal distribution on y, and this is, remember, this is just the probability that a random variable y takes the value little y. So this is where x and y are distributed according to the joint distribution p theta. You know, we're always assuming some underlying probability measure space, and these are just random variables on that probability measure space, and we're assuming that that they have some joint distribution p theta. And so this thing we need to define. So I was just reminding you what this shorthand sort of means here, and we need to choose some family of distributions for this. So since y, remember y is in some finite set 1 through m, we're just doing classification here. So this is, remember here, y was in this finite set, and we just numbered it from 1 to m. Could be any finite set. Just number it. And this thing then, the most natural choice, since this is a finite set, is just to take an arbitrary PMF on that finite set. So oftentimes people use pi for a vector. So let's see, what is it going to be? Pi y, and here pi is not the number pi, but pi is a vector, pi 1 through pi m. Pi because it's like p for probability. So we could just assume this sort of distribution, and then our parameter theta will include this vector pi. So it's just an arbitrary PMF. And that determines the y part, and now we need to think about the conditional distributions of the x's, and it was just, remember, we only need to define the conditional distribution on the ith coordinate given y. And this is, right, so reminding you also what this is the probability that xi, that's the ith coordinate of this random variable, probability that equals little xi given that y equals little y. And so for this, I'll mention, so there's lots of possibilities here, and so let's think about, we'll break them down into different cases. The first case would be, I suppose, if xi is in some finite set. So maybe we'll just number whatever finite set it happens to be. Let's just number it. I don't know, 1 to capital N or something like that. Then the natural choice would be, then, for example, you might choose this thing, p theta xi given y, to be some numbers. Let's call them, I don't know, let's call them q of xi and y. And then you would have to number, so q here would be a function from pairs xi in this set and y in this set. So there's only finitely many numbers here. There's n times m, little m numbers here, numbers that define this distribution. And so that was if it's in a finite set. If it's maybe, say, if it's in a countably infinite set, 1, 2, 3, we'll just number them, whatever that countably infinite set happens to be. Then, for example, just take any. Yeah, I mean, it's pretty much up to you. Whatever distribution makes sense for that that dimension of x. So you might choose, I don't know, maybe Poisson or geometric or whatever. Whatever makes sense for that random variable. And similarly, if it's, say, real valued, then you might choose Gaussian. That's a pretty common choice. Gaussians are always popular. Or gamma maybe, or whatever makes sense for that random variable, for that dimension. And then, so each of these, you'll make this choice, one of the, a choice like this for each I, for each of the dimensions. And so you can mix and match, right? I mean, you don't have to choose the same distribution for all the dimensions. For the x1 could be like a discrete random variable, or on a finite set, x2 could be Gaussian, x3 could be Poisson, x4 could be geometric. So you can mix and match, just choose whatever makes sense for that dimension. And then each of those, for each dimension, you will have some parameters for that distribution. And so your theta, theta is going to be, is just you just throw all the parameters of all these dimensions, all the xi's in together. And along with this pi. And then when you do your estimation, like if you're gonna do an MLE or something for theta, then you would maximize the likelihood function with respect to all of those different parameters. Okay, so that's how you choose this family of distributions. That's how you can go about choosing it. And let me mention, I'd also like to mention, well, I guess I already sort of said it, how to estimate. Well, there's another sort of interesting point here. How do you estimate theta? Well, as I mentioned, you could use the maximum likelihood estimate, or you could use a MAP, maximum a posteriori, and in that case you'd have to assume some distribution, some prior, we call it, distribution on theta, on your parameters. Another alternative, which is a little bit different than what I described, is rather than estimating theta, we could integrate theta out. So we could take a fully Bayesian approach, as they say, and integrate out theta rather than estimating. Rather than doing a point estimate, we could integrate it out, and then we could get the predictive distribution on y given x, and that would be a fully Bayesian naive Bayes. So it's a Bayesian naive Bayes. So remember, the Bayes part here was not the Bayesian. That was just using Bayes' rule. So it's sort of different types of Bayesness here. Okay, so one last point, which is, I think, an important point about this model, is to understand why we make this conditional independence assumption in this model. What's the point of that, right? I mean, we could have just as well have defined the conditional distribution on all the x's given y, right? I mean, sort of um, you know, the joint distribution on all the different coordinates given y. So why didn't we do that? I mean, what's the point of assuming the factorization? That was right. The factorization, remember, was the key part of the naive Bayes model. This assumption, we assumed that the features were conditionally independent given y. So why did we do that? Why not just define this thing directly? It would be a richer model. We could have much more interesting sort of rich. We could capture dependencies between these x's. So why wouldn't you do that? Well, there's a very good reason, and it's because you can estimate. So you can estimate when you make this assumption that this factors in this way, xd, then you can estimate theta more accurately using less data. So if you had assumed a more complicated model of this more general thing rather than the factorization, then typically it's going to require much more data to get a good estimate for your theta, or all the different parts of theta. Whereas here you're estimating d. There's d of these conditional distributions, and so it's d, and then you have for each value of y for each of them. But it's much easier to estimate these conditional distributions than it is to estimate this whole thing. These factorized sort of one-dimensional distributions than to estimate the joint thing, because this is a d-dimensional. It's a distribution on d-dimensional space, whereas these are d one-dimensional distributions. Well, times all the one for each value of y. But it turns out that this is much easier to estimate, and so as a result, your model, even if it's a wrong model, even if this was an incorrect assumption, even if this is not true, even if you know this is not true, then your model can still perform better than if you had assumed, say, a correct model, a more general model. And that's why this is an important assumption. That's why people make this assumption, because it's statistically advantageous. So that's an important point. Let me say that in a slightly different way. So a wrong but simple model can work better than a correct but complicated model. So let me write that. Wrong but simple can be better than correct and complicated. That's a very important statistical fact of life. And so here, this conditional independence assumption makes things simpler, maybe wrong, but it turns out that can actually perform better than if you had assumed the full thing. So naive Bayes, it's it's not the best classifier out there, but it's nice. It's nice and simple, easy to understand model, and it's good to illustrate some. So it's a generative model, so that's a nice thing to see.